Good afternoon. Okay, so we are going to wrap up with our last talk of this block before a break, and we will be presenting Profiling at the Speed of Light with Pablo Galindo Salgado. Take it away.
This year I was wondering, maybe it's time for me to just, for once in a while, to do a presentation, speaking slowly, giving enough time to breathe, so people can actually follow. But then I said, nah, let's roll. Cool. So I'm going to talk about a lot of profilers today, but I'm going to introduce first a mystery that's going to help us kind of motivate all of these things. So the mystery is the following. Here is some code. It does a bunch of things. So what this code is doing is creating a big array with numbers from 0 to 1,000, one by one. So 1, 2, 3, 4, 5. And then in this profiling loop, what we are doing is that we are extracting all the numbers that are bigger than 500, and then we are adding all of them together. Because, I don't know, they pay us a lot of money to do this. Very important. And this takes some time, like we can go for coffee or whatever it is. But then, I don't know, we have some new ideas to improve this code, and then we are going to shuffle the array first. In theory, the result is the same, because the numbers that we are going to add together are the same. It's just that they are in a different place in the array. But then we measure how much time this takes, and wow, there is quite a big of a difference. I mean, it's not super dramatic, but it's quite noticeable. When the array is random, it takes like 950 milliseconds, and when the array is not random, not shuffled, it takes like 600 milliseconds. So there's something going on here, because this is like 55% slower. And the interesting thing is that for the ones that you have done profiling before, you may have some ideas here, and some of them may be very beautiful, but I'm going to crush all your dreams because it's not what you think. Cool, eh? Okay, so let's see what we can do here, right? So we are going to try to understand what's going on here, and for that we need performance profilers. And there is a bunch out there, like for instance, there is PySpy, Scalene, there is a bunch that you can use. Choose the one that you want and run it, and it will tell you like what Python functions are slow here. Well, let's see. It's not really useful because both of the slow version and the fast versions look the same, because it turns out that you're calling the same Python functions, because the real, like what is going on, whatever is happening that is making one version slower is happening inside NumPy. And it turns out that NumPy is written in C and a bunch of other forsaken languages maybe that we're not talking about here. But the idea is that these profilers are only able to see Python code, and that is kind of like not super helpful. So like, sure, some of these bars are bigger, which means that it's slower, but like really we cannot understand what's going on. So for that, like we need to go deeper. We need like a better profiler. And one of the best profilers that there is perf, which is a horrendous name, because if you search this name in Google, there is going to appear anything other than the actual profiler. But the perf is a profiler that is distributed with the Linux kernel, so serious business, and it does a bunch of super cool things. In particular, perf can see a lot of stuff other than just like what is faster and what is slower. For instance, perf can see like hardware counters. It can tell you like what the CPU is especially doing. It can tell you like super low level details like branch miss predictions, cache misses, cycles. It can tell you, I think, like memory latency, how much it takes to actually read memory from RAM. But it can also provide like system calls, the kernel. Like it's basically illegal to use this thing. Like it's just really powerful. But it has a bunch of problems. So if you run perf, you can like there is 1,000 million of outputs that you can get, but like just to like give you an idea of what you normally will get, you will get something like this. It's full of like words that mean things. The first time you see this thing, you feel like an alchemist, like trying to read like some spells all over there. It's quite involved. But you can actually, I promise you, you can actually make sense of those numbers. For instance, for our particular mystery, we want to focus on some of these numbers. So again, going back to this, we want to understand why this code over here is a bit slower. And we just run perf and look at those numbers to see which ones make sense. Well, in particular, if you look at this code and then you have seen like, low-level optimization before, probably the thing that is going to come to your mind is an effect called branch misprediction. And that more or less explains the problem. And in particular, the branch misprediction is because the CPU is trying to predict what the next instruction is going to be. And when the array is not shuffled and all the numbers are sorted, basically the loop that NumPy is going to execute is going to ask every number in the array, are you bigger than 500? And for the first 500 numbers, because they are in order, the answer is going to be no. and then it goes into use 500, then 500 is obviously equal to 500. Maybe that is not true, but then like from that point on, all the numbers are bigger than 500. So the branch predictor will be very happy, and it will the CPU will do those operations even before they are actually requested. So that's cool. But when the array is shuffle, all the numbers are random. So like the branch predictor is constantly failing because like if it's checking like are you bigger than 500, it's trying to predict some patterns. There is no patterns because the array is shuffle. And that is a cool explanation. You can like talk about this explanation with your friends, and they will think that you are very smart. And it's so common that you can actually you can actually say it and people will believe it. But with perf you can actually check it, which is actually cool. And you can run perf over this example, and then you can get these numbers, and then you get these ones here. In particular, the branch misprediction is this number over here. So what we expect is that this number is going to increase in the slow version. This is the fast version. But it turns out that when you run it over perf, there is an interesting effect. So these are the two numbers that we are going to look. One is the branch misses, and the other is the total number of instructions to execute. What we expect is that when we move to the slow version, the first number is more or less the same, the second number is much higher. But what will happen is that the slow version, both numbers are higher, but in particular the instructions went up quite big. So this is not a branch misprediction, this is something else. Like the slow version is doing much more work than the non-slow version. So it's not just weird branch misprediction. And then you can say, well, that is so cool, man. Like, I'm sure that you have never said that this was branch misprediction because you know all of that about perf. Certainly not in a talk that you did in 2017 in Python Spain. You actually mentioned that this was a branch misprediction, right? Like, be careful with what you say. I'm here to redeem myself. So cool. So if you run perf, another thing that you can do is to solve these results in flame graph, because that's normally what you use to make sense of what's going on. And basically, they look like this. If you don't know how to read them, I'm very sorry because I'm not going to explain it. But what is important here is that bigger normally is worse. But what I want you to show about these flame graphs is that perf by default only shows you C stuff. There is no Python information in this flame graph. All have these funky names like pyrun simple file object. Super informative. But it is very difficult to make sense over what parts of the actual Python code is slow here. And this is the problem that we have with perf. Perf doesn't understand Python. So what we did in Python 3.12 and now in 3.13 is try to teach perf how to read Python code. So we can use this tool and all the power that it has, and you can actually have Python information. So hopefully once you have that, we can understand that. And it's not only about C. Like any compile language will have the same problem. Like perf normally understands all the compile languages, but it doesn't understand like Python, because like Python itself is written in C, and it's only going to show you like the C stuff inside. So let's talk about how we managed to get perf to understand like Python code, which is a bit of a hack. Cool. So let's go into that. So let's imagine that we have a bunch of functions. So in this case, we have like 3 functions, and at the end, like there is some CPU-intensive code that we are profiling. So we run perf over this. Again, perf is only able to see like C code. So what is perf looking at? So perf is going to see a bunch of C functions. Every time you call a Python function, normally there is a bunch of C functions that are called. Like here is a bunch of them for a specific version of Python. Obviously, we are changing this function all the time just to make this slide very obsolete immediately. But like, bear with me. Let's imagine that this is the actual truth. So in particular, every time you call, like for instance, bats, there is a bunch of functions that are called in C, and those are the ones that perf are going to record. You call another function in Python, and the same functions are getting called, etc. So the problem that we have is that even if you call bats or bar or foo, these functions are the same. In particular, the function that runs the thing is this py-eval frame default, which is a mouthful, but this is the same C function because the evaluator loop of the bytecode is always the same. It's just the data that changes, the actual bytecode that is passed to this function. But the function itself, the name of the function, is always the same. So that is why we cannot normally use perf to distinguish Python functions, because Python really is just data. Like Python is like, it doesn't exist. I'm sorry to tell you, but like it's just data. The actual reality is C, the illegal language. So our objective is that somehow we need to rename this function and teach perf that this is not this eval frame default, but it's called bats, or like bats and maybe the file or something like that. Obviously, we cannot rename the function because that will be catastrophic. But what we can do is trying to insert something like maybe in the middle of these two calls index that somehow is some C function or something that has the name of the Python function, and that needs to be unique per Python function. So it basically will look like this. Like if we could inject some kind of C frame that is unique per Python function, so it's not called always the same, between these calls, that obviously is not going to do anything, so we don't want it to do extra job because we don't want to make the like Python slower, or at least it's going to do minimal job. But what we want is that it's unique per function. So this is our objective. So thankfully, perf has like an interface to do that. It's quite funky. What perf says is that you can drop a file in /temp, and you need to name it this way. There is no other way, and it needs to be in /temp because why not? And then if you put you replace this file with the PID of the process that is being run, you need to write like a bunch of things that look like this. Basically, every line is a memory address, like a size, like the name that you want to give it. In this case, for instance, is a function called rm3, and in case you can put any name. So in particular, what we're going to do to distinguish it from C stuff is to prefix it with like pi : the name of the function and the file, because why not? And what this is representing basically is like a memory address of some code that you're going to place in memory, and how much size is that, how long is that code in memory. And basically, the idea is that we are going to create these codes, we are going to place them in memory, and then we are going to teach perf how these codes are named using the information drop in this file, which you can actually read, it's just text. Obviously, you need to put like some code anywhere. So what we did is like we have this minimum assembly code. I almost have like a joke that in any of my talks in PyCon, I saw assembly. It's not on purpose, it's really needed. But here, like, it doesn't, you don't need to understand anything here. The only important thing is that this function is just calling the next function. It's just doing that and a bunch of backkeeping. But the idea is that we are going to copy this function again and again and again in different places of memory. The actual code is going to be the same because it's not going to do anything special. It's just going to call the next function. We are going to assign in that file that I showed you a unique name every single time we copy this. And every single time there is a new Python function that we need to call, we're going to create one of these codes that they look the same, and they are going to change the name in the file. And that's how perf is going to know how this goes. Obviously, this is a bit more complicated because the time you're writing assembly code by hand, you need to do it per architecture. So we have right now a version for like x86 64 and for ARM that is a bit more it's a bit bigger, but it's not super complicated. Obviously, you can say, wait a second. So to fix this perf stuff, you're basically writing like assembly code in memory, and then you are writing this thing on the heap of the process, and then you're marking that as executable. This is a JIT compiler. This is a JIT compiler, right? Okay, yes. And so let me tell you something. This gentleman over here is Bram Booker. So he has a talk on Sunday. You should go there at 1 p.m. at Ballroom A. So this gentleman over here is fantastic. This guy is creating the actual JIT for CPython, the big one, the one that is going to make it faster, right? So yes, Bram, that is very cool. But I have something to tell you. I was first. Even in my JIT is stupid, but like, it's technically JIT compiler, which is what is important. Anyway, so that's the idea, right? And once you have this, perf is able to just grab this information from the file. It's going to relate all these unique like frames to the actual names, and suddenly you can just finally have this to convert this flame graph, which only has C functions over here, into something that looks like this. When suddenly now there is this pi : sum and the file over here, and then you can know what function is there. So you know all the C code that is being run by NumPy, but also you know what Python functions is being called. So for instance, if you want to just follow the Python functions, you can just look at the frames that start with py : and then you can see like what is calling what. This is the most complete version that you can have because it's showing like C and Python at the same time. But obviously you can filter this to by name, for instance, and only show the frames that have py : and then you have a Python only profiler that is extremely fast because perf is really fast. But especially if you're doing C extensions with Rust or NumPy or whatever it is, or if you are like having problem with C extensions that someone else wrote, which is more common, then this will teach you the whole thing, which is fantastic. Well, there is only a problem. I lied. This doesn't look like that. If you run it with perf over NumPy, it looks like this, which is really bad. There is this mysterious friend called unknown here, which is like really bad. Like, it doesn't look like this. So it's a mess. This is a lie. Why is that? So why doesn't work? Well, it turns out that there is two ways to get the stack in C. Perf supports two ways. One of them is frame pointers, which is the one that we added in 3.12, and the other is using debugging information, which is much, much harder. So frame pointers are kind of nice because like it's a very easy way to obtain the stack trace in C. Basically, the way it works is that there is a register called the stack register, and the stack register basically has like a linked list in the stack of the process that basically will tell you who is the caller. So basically, to unwind the stack in C is very easy. I mean, very easy if you know what you're doing, obviously. But like basically, you first register, and then you start like following the linked list in memory and looking at the previous address to know where is the function that is being called. And this is what perf is doing, and this is extremely fast. It's really, really, really fast. If you actually go to the internet and you go into the profiling space, compiling applications with frame pointers is what makes profiling really fast, and that is great, and that is the support we added. There is only one problem with this approach, which is that nobody does this. The reason nobody does this is because this is using this register over here to keep this linked list, but this linked list is only in use if you actually unwind the stack, but normally you don't do that, and a register is very tasty for compilers. They like registers. So do you know what you can do with these registers? You can put other stuff in that register, and that is what most compilers do, unfortunately. So if you use these registers, you can generate better machine code, and therefore Python is, and any other program, is a bit faster. That is why almost no one compiles with frame pointers, unfortunately. In particular, if you compile with frame pointers in Python, you are stealing one register from the compiler, and the code is a bit slower. How much slower? Well, if you compile Python normally and you call that 100%, then you lose around 7% in the most dramatic case, which is when you compile Python with frame pointers. To do that, you need to pass like a bunch of like options to the compiler that nobody passes, so that's why it fails. But you know, if you are able to get this 7%, which many companies, by the way, do, like for instance, Meta compiles stuff with frame pointers and many others, just because profiling is very important. But normally, if you go for Python in Ubuntu, the Ubuntu doesn't go with frame pointers because they care about speed. You know, so that's unfortunately, that is why it doesn't work. So the other way is debug information. So debug information is the kind of binary information that compilers put there just to make sense of the like super complicated assembly that they generate. And perf has a super insane way of supporting debug information if you are able to write it. Unfortunately, I'm not going to teach you how to write debug information, but I'm going to show you the horrors that how they look. It's really annoying. Like you have all this insanity going on there. This is part of the CPython support here. You need to like list all the registers and write by hand. You have like to write like nice diagrams, otherwise people are going to call you crazy and they don't know what you're writing. And also like it's quite annoying because like when you try to debug this thing, instead of like perf telling you, hey man, your assembly has this problem in line 3, maybe you should check it. It tells you like, yeah, no. Like, nah, it doesn't work. So that doesn't tell you anything about what's going on. So it's really annoying, but we did it. And now Python 3.13 will support actually dumping debug information, so you don't need to compile Python with frame pointers anymore, and you can use NumPy from PyPI without having to recompile it yourself with frame pointers. You need to run an extra step. So normally when you run perf, you need to record data. So for instance, here's a command that you can run with perf record, and that's the way you record data. Now you need to pass this option called call raf equal dwarf. You don't need to copy this slide. It's all over the internet because nobody compiles with frame pointers, so everybody tells you to use this. But now you need to run like an extra step, which is the augmentation step. And what perf is going to do is that it's going to grab all this debug information that we are writing to a specific file, and it's going to complete the result file that perf normally generates with this file. If you look at what actually is happening here, you will cry. Because like, among other things, perf will create a bunch of like binary objects in this last temp that has weird names, but you just need to ignore it and smile. And once you do that, you can actually just run perf report as you normally do, and it just works, which is great. Is this like the best thing you can do? Not really, because it has some downsides, but you will see. At least it just works by default. So it's not really the best. Like it basically depends. It has a bunch of problems. For instance, one of the problems that it has is that to do to use this debug information, perf needs to copy the stack every single time it takes a sample, which is a bit annoying because like the result files are super big because they contain like entire copies of the whole stack of the application. Also, it cannot unwind nicely with frame pointers anymore, which is really fast and really efficient. It needs to just leave unwind, and that is quite slow because it needs to do it from user space. So normally you cannot use perf at full speed. It's still faster than any profiler normally that you can use, but it's still not as fast as if you have frame pointers. And also, like unfortunately, if you have like a super big stack, because you know you have like a ton of functions in the stack, it's not going to copy all of them. So you can have like incomplete stacks if you have like super big like applications. and also like it leads to longer processing time. So it's not the best thing, even if like writing this dwarf is very difficult, but at least it works if you don't want to compile everything with frame pointers. Things are changing. For instance, Ubuntu is moving to compile everything with frame pointers except Python, because Python is a bit slower than other applications. Because normally frame pointers, the slowdown is like between 2 and 3%. In Python, it's a bit bigger for reasons, but hopefully we can fix that in the future so people can go back to frame pointers, which is what everybody should do. But now in 3.13, because you probably don't care about any of this, you can use this dwarf and it will just work, which is cool. So to activate this and to activate perf support, you have two environment variables. You have the one in 3.12, which is called Python perf support. You can set that to 1, and Python will start writing these files, and you can use perf with that set. In 3.13, you can use Python perf JIT support, because we like to add all these underscores that are possible. We gain more money the more underscores we put in our environment variables. And it will emit the JIT support. So if you're planning to use dwarf, you need to select the appropriate environment variable. If you want to use frame pointers, it's the first one. You can also, instead of using an environment variable, you can call Python with -x. In the case you want to use frame pointers, you can use -x perf. If you want to use the dwarf, you can use perf underscore JIT. I put JIT so Brand knows that I was first. Because I could put like perf dwarf, but perf JIT sounds cooler. It's also the name of the interface, so you know. That's not the real reason. But yes, that's the way you will activate. So just to be clear, before Python 3.12, there is nothing, no bueno. In Python 3.12, we added perf support with frame pointers. So if you are brave enough to compile Python yourself with frame pointers and every other dependency that you have, then you can use it, which a lot of people actually do, by the way. But now in Python 3.13, you don't need to do anything like this. You can use dwarf if you're able to pay the extra cost, and it will just work. Cool, that's awesome. And now using this dwarf or frame pointers, you can get like entire flame graphs with both like Python and C. But obviously, as I mentioned before, if you don't like the C, you can just filter this by Python, and then you can get super compact, nice Python like flame graphs that will tell you like what functions are slow here. This is, for instance, a snapshot of the test compile in the Python test suite. So that's awesome. Okay, so let's use this knowledge to solve the mystery of the slow NumPy function. So we run perf with frame pointers or without frame pointers, and then we get this beautiful frame graph. So now we can see like that. For instance, the part over here is like is about this NumPy, the module level functions that are happening, and we can see here that this is the array subscript function that is taking like the numbers that are bigger than 500. So this is the slow version. As you can see, this became like this is the fast version. This became super slow. So whatever is happening, the difference is over here. So you can zoom onto there, and you will see that this is the fast version and this is the slow version. So the slow version has this extra function over here and this extra function over here. So to know what is going on, so now we already know what's going on. It's something that has to be with the like filtering the elements that are bigger than 500, and whatever is happening is this function over here, this contig to contig that is in C. So we now know where to look to. So there is many ways to look to that. So it's this function over here just in case, but there is many ways to do that. One thing that you can do is to use a debugger to know what's going on, or like how many times are you calling that function. So that's a thing that you can do. So for instance, but you can also use perf. So in perf, you can say, I'm going to put a probe in that function. So you need to call this command called perf probe with a bunch of like weird things. But at the end, you say, I want you to tell me every time you call this function that we want to investigate, this contig to contig. And then you call perf record, and perf is going to take a snapshot every time it calls this function. It's super cool. And then you check how many times that has been called in the fast version, and the answer is 1. And then you check how many times that has been called in the slow version, and the answer is a lot. It's like, wow, how is that possible? You can attach a debugger. For instance, this GDB script that basically is going to put a breakpoint in contig to contig, and it's going to print the only argument that this function has, which is called dimensions, which is, I don't know, a number. And if you call it with the slow version, you are going to see that it's being called a lot of times with very small numbers. But if you call it with the like fast version, it's going to call 1 with the number 500. Okay, this is the answer. The reason the slow version is slow is because it's copying memory a lot. It makes sense. In the fast version, to extract the numbers that are bigger than 500, you can just copy all the contiguous memory from the start to the 500 because they are all in memory together. And NumPy, which is very cool, uses vectorized instructions, which are very fast, and it just calls these functions once in a very efficient way. But the slow version, because the numbers are shuffled, to reconstruct an array with the numbers that are only bigger than 500, it needs to copy a bunch of numbers one by one, sometimes 2 at a time, and it calls this function a lot of times, and that's the reason it's slow, which is quite cool. It's useless knowledge, but like, you know, mystery solved, mystery solved. Nice, we did it, thanks to perf. Cool. So I want to show you some of the other cool things that you can do. Obviously, this is just as an example to show you when using like knowledge of C and Python at the same time is very useful. So to understand like what NumPy functions are doing and what Python functions are in the middle. But you can do super advanced stuff. Obviously, this is not your go-to profiler. If you just want to know why your Python functions are slow, you can use a normal profiler. But if you have like compile code in the middle, or you are doing C extensions, or you are dealing with like high performance computing, using this is fantastic. Like you can do a bunch of super cool stuff. And let me show you some examples of things that you can do. Since perf can see basically any C function, and you can ask perf to basically trace any C function at full speed almost, you can do things like, oh, please tell me every time you try to acquire the GIL, and tell me every time you finish to acquire the GIL. So you can basically have a flame graph that will tell you which functions are waiting for the GIL more time. So you can run perf, and then you can get like output that look like this. So for instance, you can tell me what Python functions, obviously there will be C functions underneath, but if you just want to see what Python functions in your code are waiting for the GIL more in a multi-threaded application, you can run perf, and it will tell you, for instance, that this is the Python test suite, so this is real data. So that this check cache is basically waiting for the GIL in this case 1 second. So this thread is blocked 1 entire second, and you can start looking about like what is going on there. So maybe you can have a different GIL acquisition algorithm over there. You can obviously have a different output over here. You can plot it over time, and then you can see like the GIL switching point. So for instance, here's like 2 threads that are fighting for the GIL, running some computation, and another thread here is sleeping. So you can use this data to basically plot like how the GIL is being bounced between these threads around, and like how much time is every thread bouncing for the GIL. Because what perf is going basically giving you is raw data, and then you can put some effort into like plot it as you want. You can obviously do more things. So for instance, this flame graph looks like a normal flame graph of how slow the functions is, but instead of like taking samples and doing a performance profiler, what I'm asking perf here is basically what functions are dropping more the GIL. So this is not how much time are they waiting for, this is how much time they are actually dropping it. So here, the bigger horizontal bar is the more times that particular function drops the GIL. So you can use this thing to, for instance, to file GIL contention points if you have an application that uses multiple threads in C++ or C and is calling back into Python a lot of stuff. For instance, this is actually, yet again, is the Python performance suite. I think this is test async.io, and you can see actually how, for instance, the GIL is dropped in epoll select, which makes sense because we need to drop the GIL around that function. In this case, you can even see the test case is base test or whatever it is. Sorry, okay, here. You can also do other things. For instance, you can say, I'm going to put a probe in GC collect, and you can do the same thing, and you can like run, for instance, in the test suite, and you can find what functions are calling the garbage collector more. So this is not how much time they get into the garbage collector, is how much time they trigger the garbage collector. So you can use this, for instance, to detect like functions that are allocating a lot of cycles themselves, and they are triggering the collector a lot. So for instance, once you understand what functions are doing this, something that you can do is deactivate the collector around the function, so the cycles are only cleaned once in a very efficient pass, instead of like calling it again and again and again. Again, this is real data for the Python test suite. You can see that obviously the function that calls more the garbage collector is calling the garbage collector, so that's the first one. We do it obviously in the test suite for reason. But here, for instance, you can see that this test called test task del collect in test async.io, evil_del, is calling the garbage collector quite a lot. Well, indeed, it's evil, but you can use this in your real applications to gain money or whatever you want to gain. It's very cool. Obviously, you can use this data in even more efficient ways. So there is a lot of GUIs and other applications that can read perf. And this is the actual power of perf. That is not just a fantastic profiler. It's that there is already a huge ecosystem of tools that just read this data. And because just perf now will automatically read the Python stuff, it will just display the Python stuff as is any other C frame. So for instance, you can use Hotspot, which is an application for Linux, I think, that can read directly the perf files, and it can show you, like, for instance, every thread, and it can show you the flame graph for every thread, so you can actually look at the data in many ways, not just the raw output. But you can also use it as a normal profiler. For instance, this is an example that you can do. You can run perf record, and you can pass like a bunch of frequencies. For instance, we are going to use here frame pointers as the stack unwinding because it's faster, and I'm going to benchmark a file called benchmark.py. So the output will basically look like this, right? So it's just to show you here that you can have other things than the flame graphs. And here you're going to see the Python functions here in the middle, and they start with py : So for instance, as an example, imagine that you have this example. This example is from the real Python coverage of this feature. It doesn't matter what it does. It calculates a bunch of like luminance given an image. But this is slow. And then you run perf, and what you will see is that most of the time, this is spent on statistic.py, particularly 97% of the runtime, and that is spent on the underscore sum function. So something that you can do is basically, instead of using statistic.py here, like the mean function for statistic.py, which is slow. The reason it's slow is not because we are lazy, it's because we need to be correct, and correct normally is slower. But you can implement your YOLO mean, which is basically adding all the numbers and dividing by the number of numbers in a lambda, and this is much faster because it's incorrect in many cases, but it's faster, which is cool. And now you can run it again, and you can see that you go from 97% of the time to much more slower in the actual file. So benchmark.py, that particular function now is 0.58%, which is obviously much faster. Now the time of the script is being spent elsewhere. So that's a way to use this just with raw output to optimize it. Obviously people like graphical stuff, so maybe this is not the best way, but this is just to show you that you can do it without abandoning your terminal, which is very cool. And this is basically it. I hope that you more or less get an idea over like how you can use perf, and that is how powerful it is. This is more powerful the more tools you build around. So something that we want to do is to build like an ecosystem of stuff that you can use directly, because perf is quite low level. So it's not like just prepare most of the time to just run it and get information out, although as you can see, you can do it. This is more powerful the moment you use this data to plot it in different ways, or to represent it in different ways, or as part of like more advanced tools. And we hope that with time, people start to use more and build tools around this to just basically unlock the power of analyzing like both Python and C at the same time. But this is just like a sneak peek of what you can do already. And I hope you have enjoyed the talk and you have learned a bunch of things. And I really tried to speak slower this time, so I hope that I have achieved it. Thank you very much.
Okay, we don't have any time for questions, so if you have any questions for Pablo, catch him in the hallway and ask him there. Thank you very much, and we do have a break now, I believe, for the next 30 minutes before the next talk slot.